Welcome everybody to our Tuesday afternoon EOL seminar. It's my big pleasure to welcome Zhaoxia Pu.
Yes, that's good.
She's from the University of Utah and visiting us here just for the day, I believe, right?
Right, tomorrow.
So it's a big pleasure to have her here. Zhaoxia's primary research interests are atmospheric data assimilation, numeric modeling, and predictability, with specific topics on satellite and radar data assimilation, mesoscale, severe weather systems, observing systems, simulation experiments, targeting, weather observations, atmospheric boundary layer over complex terrain. Quite a handful. Zhaoxia received her PhD in meteorology from Lanzhou University in 1997. Although she did most of her PhD work at NOAA NCEP in Washington, and even continued there as a UCAR fellow, a postdoc fellow, afterwards. From there, she moved to NASA Goddard and worked 6 years at UMBC and NASA Goddard as a contractor there, before she then moved to University of Utah, where she's now a full professor at the Department of Atmospheric Sciences. She has authored nearly 80 peer-reviewed journal articles, participated in over 10 major field programs. She won an Outstanding Research Achievement Award from the Mesoscale Atmospheric Process Branch of NASA Goddard, and she also received an Outstanding Faculty Teaching Award from the College of Mines and Earth Sciences at the University of Utah. Today's talk is Progress and Prospects of Radar Data Assimilation supporting hurricane research and forecasting. And I'm looking forward. And please, Zhaoxia.
Thank you, Hog. Thank you for the introduction. Good afternoon, everyone. So it's my great pleasure to be here today to give a talk. So the title of the talk is Progress and Prospects of Radar Data Assimilation, but I know at EnKF we have any expert work on the data assimilation, especially radar data assimilation. We have world-class scientists sit in the audience. And also, in terms of the many people work on the develop of the data assimilation methods. So I have collaboration with EnKF scientists. So here I would like to acknowledge all my collaborators, and also several of my former and current students work on the radar data assimilation. So really, all the results I present is my students' work. So the outline is here. So I will say, so my talk is about the radar data assimilation supporting hurricane research and forecasting. So because radar is very important observance system for the studies of mesoscale severe weather system and the convection, but hurricane is specifically outstanding case. So when I talk about the recent progress and the challenges, I'm not going to address this methodology, and I'm not going to address this retrieval method and all of this, and also not the observations, but the purpose of my talk, since this is a EOL talk, I would like to address what's the link between the observation and the modeler through the data assimilation, and I'd like to just make a few points to see how the various kind of the data can make the influence, and what we still need as far as data processing and the data assimilation. So I'm going to show you some of the results about the assimilation of the radial velocity compared with reflectivity, and also the influence of the quality control, and the radial velocity versus retrieved wind. So even the retrieved wind come from the radial velocity, so that may make a different information flow. And also we have simulate this radar reflectivity, so we have this cloud analysis can also used for that purpose, and we can see what's makes differences And I will also talk about some of the recent challenges about the dual-pol radar data assimilation, and just give some prospects about the next generation airborne polarimetric Doppler radar for the hurricanes. So as I said, I will be more on from the numeric weather prediction perspective, and also give our statements here. So airborne Doppler radar as an essential part of the observance system. So they are very important, as we can see. So first thing is, so radar data now becomes conventional because we have this available NOAA Next Radar network. So we receive data every day, and which provides significant information about mesoscale convective system, hurricane, and the clouds. And also during the hurricane season, we have airborne Doppler radar become operational. NOAA each season they fly, into the hurricane. So this is an example showing you the Hurricane Sandy in the year 2012. So you can see how much we get this radar coverage. And so most notably, so last year during the Hurricane Harvey, so Science magazine made this cover page, and they just said Hurricane Harvey provides a laboratory for the U.S. forecast experiments. So this is HRD radar observation during the Harvey, so we can see what's come up. So except the satellite data, so we radar really sample very detailed hurricane structure, and it becomes very notable not only in the science but also in the public. So what we are so far in terms of use of this radar data in the numerical weather prediction. So this figure I borrowed from Minjin Tong. So she actually gave a presentation showing this is results in the year 2015 when they make this Tail Doppler Radar data as part of the operational data assimilation in the NOAA HWRF model system. So HWRF is Hurricane Weather Research and Forecasting Model, which is currently the regional high-resolution operational model for the NOAA hurricane forecast. So as you can see here, so this black curve is best track intensity. And so without this TDR in the core data assimilation, so you see this red curve. So you can see how much distance they have. But if you assimilate this TDR data for this particular case, so this is purple line, you can see how much progress this TDR data can make in terms of the hurricane intensity forecast improvement. And so this is particular for the Hurricane Isaac in the year 2012. So they also found so there are significant improvement in the hurricane structure when assimilate these radar observations. So this is good. So because radar provides hurricane inner core observation, so that are essential for the hurricane vortex initialization in the NWP. So this has already been proved. So it's not just a concept now. So after next 20 years, so I think when Jenny first published her 40-hour paper in 1993, so that's the beginning. But so now, so it's operational. But still, we only use very limited radar information in the NWP. So not only because of the quality control reject many of the data, but also we only assimilate radial velocity in the operational HWRF. So no radar reflectivity data are assimilated. So there are still large area for the further improvement. So as for the radar data assimilation, we just in the business to begin in terms of the operational, because it's just become in the operational. So I think in my talk today, so I would like to just showing some of the sample study from my students' previous research, and they just see, so in which direction, if we, as an observational scientists, and also the data assimilation or NWP scientists, how can we work together to make this improvement? So this is a major point I want to talk in today. So for this seminar. So just for first things, I give a very brief introduction to the data assimilation. So I use this four-dimensional data assimilation, variational data assimilation as an example. So as you can see here, so for this four-dimensional variational data assimilation, we try to minimize this cost function, which actually include, so for the model background, model analysis field to fit into what model forecast, short-range forecast, which is background. So we measure the distance between the analysis and the background. And then another thing is we use this forward operator to transfer the model variable into the observation location and the type, and then calculate this innovation. So which means so the differences between the observation, so this is Y here, and also the model generated observation. And for 4D we use multiple time data. So then because we know the background and the observation both had error, so we don't know the exactly, but we know the statistical. So then statistically, so we have this background error where covariances to just determine how much we trust the background, and then so we use this observational error variances to just scale down these differences to determine how much we trust the observation. But this B and R not only the weight of fact, but also that gives how much we trust each side, and also because this background error covariances should have a structure, so we can determine which location we trust the observation more. And more importantly, because this is a weighting factor, so they bring these two in the same magnitude. So then when we minimize this function, so we can finally achieve an analysis which is not only consistent with model dynamics, but also close to the observation. So this is a goal. So we see the data assimilation makes a combination between the observation and also the model forecast. So that's kind of like extract the useful and all the best information from the model and also the observation. So there are many developments recently regarding to this 3D data assimilation, variational data assimilation, 4-dimensional variational data assimilation, and also ensemble common field 3D EnVAR and 4D EnVAR. So all these fancy words, so you might heard or not, but most of these things explain the same thing. So how we best utilize the observation into the model and combining all the information together. So this is also the theme we would like to talk in our research. So then, as I said, so I'm going to show some of the example on these aspects. So first thing, so regarding to the radar data assimilation, so for the airborne Doppler radar data assimilation, so what is the impact we expect from this radial velocity and the reflectivity? So here we have a paper published in the year 2009 with Jenny, and so to assimilate this NOAA P3 Doppler radar observation. So we have this case for the Hurricane Dennis. So we assimilate radar reflectivity, and at the same time also they have the retrieval, the U and the V component. So here is an experiment setup. So by the time we assimilate all conventional data and some satellite data into our gas field, so to make the first guess, and then we predict to the time we have the 1 hour radar data available. So then we assimilate this data for the different configurations. So in the first experiment, assimilate reflectivity, and the second one assimilate wind only, and then the third one assimilate wind and reflectivity. So then we checked the results. So as you can see here, so this is assimilate the radar reflectivity data certainly contributed to adjustments to the temperature and the moisture field. And so assimilate this wind data certainly more contribute to the change of the inner core wind structure and the asymmetrical structure. And in terms of the forecast impact, so what we found is, so this is, you can check the paper for the details, but the message here is assimilation of the radial velocity resulting in a large impact on the track and the intensity forecast. So this best track. So you can see. So these are the two from the two curve from the assimilation of the radial so the velocity. So it's UV component here. So yeah, and so then and also it actually improves much more on the intensity as well. But for the reflectivity, we really didn't get much impact on the track or the intensity. But if we assimilate both this velocity and the reflectivity together, so we can certainly get much better results. So then what's the contribution we see from the reflectivity assimilation? So we compared this 3-hourly accumulated rainfall over the storm region. So as you can see here, so this is trim satellite measured rainfall and for this time series, and then so this is the black curve here is control. But if we assimilate only this one information, we did not make much impact on this accumulated rainfall. But if we assimilate the radial, the reflectivity, or assimilate this velocity and the reflectivity together, we get much better precipitation. So then this is to say, so this reflectivity and the radial velocity so really contains a different information. So if we do not consider so how we actually use each of these, but based upon the current technology we have, certainly so this reflectivity seems more important for the precipitation forecast. But radial velocity through this change of this divergence and convergence field, it can contribute to the precipitation, but its influence still cannot fully compatible with this assimilation of the reflectivity. So this is first thing. So certainly both of this information are important. And then the second thing is, so for the we work with Dr. Wencheng Li, and so try to get to see how much we can get from this radar data simulation in terms of the quality control. And I have a student who work with him during the summer and processed the radar data for one of the TPARC 2008 case, so which is NRL P3 airborne Doppler Radar observation, so which is for the hurricane super typhoon. It is a typhoon over the Pacific Ocean, so typhoon Genesis case. So we actually get this radar data, and I can show you the example. So we did the QC threshold for the 3 different thresholds. So the low, medium, and high. So which means no threshold announce more data past the quality control, and high announce only high quality of the data. So then you will see after the quality control, the data coverage in terms of the reflectivity and the radial velocity, they are different. So for the no quality control, you keep more data, but for high quality control threshold, you actually just have the less data amount. So we have a paper document these results, but I can show you quick here. So what we found here is, so again, assimilation of this radial velocity has significant impact on the overall forecast, because here, as you can see, so this is top, so left, this one is the track, and this is the intensity. So the black is best track data, and so then the red is control without this radar data assimilation, only conventional data assimilation. And then so the so this blue is reflectivity data, and then so the green is for the radial velocity, and this orange, so yellow line here is reflectivity and radial velocity together. So you can see reflectivity and the radial velocity together makes largest impact. And for this particular case, so radial velocity gives still significant impact, but the reflectivity still kind of just small impact. So same thing for the intensity. But most notable thing I'd like to comment here is without the radar data assimilation, so the Wolf model here did not predict the genesis of the null ray, but with the radar data assimilation. So all the experiment predicts the genesis of the null ray. But in terms of more notable results is here. So the message is the influence of the data quality control. So what we're seeing is if we use bad coverage but no quality of the data, we get bad track forecast. So, but if we use the high quality, but this high quality data, we get the more impact on the intensity. So this low quality data has less impact on the intensity, but better impact on the track. So then we just comment, so there might be some of the trade-off between the radar data quality and the data coverage is necessary in the practical application for the different purpose. So if we would emphasize on the track, we might want the bad coverage and give the low quality control, let more data to pass the quality control. But if we would use care about this intensity forecast, high quality data certainly is very important. But also, I think we also need to work hard in terms of the data assimilation to try assimilate this low quality of the data. But also certainly improve the quality control algorithm, get more data to be kept, still can be used, and so that's also very important. So that's why I said, so QC is really the key thing here. And in terms of the radar reflectivity, so we can see here for the radar reflectivity still, if we do the high quality of the QC, it actually, we get more benefit, and the reflectivity, even it's not contribute much on the intensity improvement, but here it's still contribute to get the better rain band for this hurricane. So in terms of the hurricane structure and the precipitation forecast, so reflectivity is still important. But the impressive thing is here, so this is the control you see in the rainbow structure, but even the low quality radar data, so yeah, if you assimilate them, so you still get good rain band. So I think it's pretty good. So good example to show the value of this data. So then the next study we did with Dr. Lee, and so for this case, so we did the assimilation of the radial velocity versus the retrieval wind component. So we know that this retrieval wind component, U and the V component, come from the radial velocity. But we just want to see so how we utilize this information, and so what's the influence we get from the assimilated radial velocity versus retrieval wind. So even if they come from the same source, they have the same information content. So this is a case still, so for the neural case, but so this is still P3 Adora data. So we use the 4D for this case, and as I showed you at the beginning, so I explained this cost function, and we use multiple time data. So the control simulation here is we derived from the GFS, but to be exactly, so we actually use the GFS as derived as the initial, and then we do 6-hour forecast assimilate all the conventional data, and then for rest of them we assimilate either UV retrieval when or the radial velocity directly. So as you can see, so it's even this UV component derived from the RV, so the radial velocity. So the impact to the track and the intensity are not equal. So it's different. For this case, so black again is this is best track, and the red is control result radar data simulation, and the green is U and V, and so blue is RV. So you can see for the intensity, so RV actually makes the large impact. But in terms of the track here, so if we check the track error, so you will see for the assimilate this UV, actually we make the best track forecast and then assimilate the radial velocity. So there are some information from the radar, but one is the original radial velocity, the other one is the UV we sample this retrieval. So there are actually have the different. So then another experiment is, so we said, okay, so if the influence are different, so can we assimilate so these two together? So we played our experiment, so which we assimilate this this radial velocity first. So this is, we believe the radial velocity more contributed to improve the inner core of the hurricane. And then, so we assimilate this UV second. So just assume which is more contribute to the environmental flow, because remember we showing the results. UV have the more influence on the track forecast. So we just try to see, okay, so if we assimilate radial velocity first and then UV second, so what happened? So you can see here. So similar to the last results, so this is the black is best track. So this is the intensity in terms of minimum sea level pressure. And so this is red is control, and the green is UV, and so this blue is RV. And but surprise, you see this orange line is RV first and then UV second. So you can see we actually made this match to the best track. So it gives the best results. So this actually kind of like showing the example. So if we use this data, so even they are come from different source, but if we process them differently, so they are represent different scale of the information. So then in this regard, so yeah, how we can best utilize our data. So this is still something in the future we can work on. So I'm going to skip all these details, but you can check our paper in the year 2014 in JMC. So then, so far, so what we've seen from all these experiments, so this radial velocity, all this UV component would have the large impact, but the reflectivity only the matter for the precipitation. So then there are people work on this direct. So we are directly assimilate this reflectivity. So as we all know, so for the reflectivity, it's a reflectivity, but model variable should be associated with a reflectivity. Use this forward model. And so then there are challenges in direct assimilation of this reflectivity data. So first is quality control. And another one is for many of these this radar reflectivity, so we have attenuation problem to deal, and it's harder to make the correction of the use of this information. And also forward model is always had uncertainty or limitation. The other thing is the microphysics in the numerical model by nature, it's also always very uncertain. So then in this case, seems direct assimilation is quite challenging. So some other people will do the cloud retrieval. They said, okay, so we just kind of build in this cloud retrieval into the data assimilation, so just perform this cloud analysis. So that's the other way to assimilate this reflectivity data. So then in terms of the reflectivity data assimilation, I think it's much less mature than the radial velocity assimilation. So we're still kind of like have a lot of explore, but I think first thing is let's see how the important this microphysics for the hurricane forecast. So this is a paper we published with my student year 2008 in the Month Weather Review, which we use the WRF model to simulate Hurricane Emily in the year 2005 during the NASA TCSP field program. So here this black curve again showing the minimum sea level pressure as intensity. So then we use a different WRF macrophysics scheme from this simple warm rain and simple ice to the lean macro scheme, and so all of this scheme different by the how complicated the assign for the different cloud property. So as you can see, so there are significant sensitivity. So if you use a different cloud macrophysics, you get a different intensity for the hurricane. So, and also if you check this hydrometeors, so they are certainly very different. So we know this hydrometeor associated with this latent heating, they can also feed back to the dynamic field. So there are a lot of influence to the hurricane dynamics as well. But I just want to use this example to show how important this macrophysics. And also another point we should note here is, so there are strong uncertainty in terms of this macrophysics scheme in the numerical model. So we don't have perfect solution, and each of them are very different. So then this also makes very difficult in terms of the reflectivity data assimilation. So what kind of forward model we should have? So that's really depend on the different scheme we use. But so the question we ask here is, what are the outstanding issues in prediction the hurricane? So we show several cases with this precipitation, but learn from last year landfall hurricane, so Hurricane Harvey. So you can see here, precipitation is notable question. So in addition to predict the intensity of the hurricane and also the track to just predict when and where it's going to be made the landfall, but in the meantime, so precipitation is a notable issue. So how can we get the precipitation right? So I think the radial velocity can contribute some, but as the previous all the case study you see, so really in order to make the accurate precipitation, so we need to assimilate reflectivity data. So this is not just for hurricane, but in fact in the NWP question in general, precipitation forecast is very challenging. So the common problem is, so we usually do not have cloud initialization for many of NWP models. So we begin from the zero cloud and we spin up our model and to get this cloud information. So it's usually takes long time. For hurricane, this can be very outstanding question. So now since we also required to do the cycled data assimilation if we do not do the cloud initialization. So it can really harm the hurricane forecast. So this becomes very important. We do this. So first thing is this microphysics has uncertainty, and the other things we have problem to just get the cloud initialization, but we have this next radar data available, and we also got the airborne radar data. So can we do the cloud initialization with the radar reflectivity? So the NOAA ESR has this GSD scheme, so which is a cloud analysis scheme, so which has you can input the 3D reflectivity into the model, and so it will modify the 3D cloud cover and the cloud tape, but in the meantime, so note that so this scheme could also combine with the satellite observation to make this more accurate. And then so they use this radar data to retrieve this hydrometeor in terms of the rain, snow, hail, grapple, and those. And then so because the adjust of this hydrometeor, so they also adjust this latent heating profile at the same time. So not just for the hydrometeor, but also for the latent heating. So we actually use Hurricane Earl as a case study and just apply this for the hurricane and to see if we can actually get some influence from this cloud analysis scheme performed as a data simulation. So certainly, so for the experimenter, just keep in mind without a cloud analysis, so we don't see the cloud at initial time, but with cloud analysis, we see the cloud at initial time. So there are spin up problem certainly also, but so still we get something good. So here is the influence of this cloud analysis. So this is a cross section for the hurricane we study. So you can see this is control. This is with the cloud analysis. So there are we get the increment from this cloud analysis. So in terms of the rainwater mixing ratio and the snow water mixing ratio, and also so the this temperature anomaly also got adjusted. So the good thing is for this case, so this is adjusted to the warm core region. And so we looked at this data simulation impact. So just for the different type of the combination. So you see this is radar reflectivity as observed by the radar. So so this is a control simulation. There are overestimation of the cloud in some of the region, but with this cloud analysis combining with this radial wind data simulation, so you see we get improvement. And so specifically, if we combine this cloud analysis of the reflectivity with radial velocity, so we get the largest impact here for this case. So, and also the precipitation structure as well. So yeah, the message here is really so assimilation of the radar reflectivity information is essential for the hurricane precipitation forecast. So if you look at this specific case, you can see, so without this radar reflectivity assimilation, so you actually compare with this satellite map, so you lose some of this rain band information. But with the radar reflectivity assimilation, you will get some of the good agreement. But with just the radial velocity or wind assimilation, so you did not get these whole benefits. So I think this example again showing for the precipitation, this reflectivity information is very important. So then now, so the question here is, so reflectivity is really kind of like seeing we do the cloud analysis, we can partially showing this, and we directly assimilate reflectivity can also get benefit, but why we cannot get for the intensity? So this is still something we should ask. I think it's raised a lot of question in the future about how we process this data, and also in the data simulation, how can we better utilize the data. But in the meantime, so we are now moved to this dual-polarimetric radar time. And so this dual-polarimetric radar really give us much more information. But so far, so I searched the literature, so we have a lot of this dual-pol radar data available, but this data assimilation is still in a very relatively new area, and very few, I didn't find them. So almost I didn't find any for the hurricane study yet. So, but if we would care about this landfall hurricane, so this dual-pol radar should actually see the hurricane before it approached the land. And so for the landfall hurricane, this precipitation becomes very important. So then how can we use this dual-pol radar information really becomes a science question and a big challenge for now. And so, yeah, as you can see here, so in addition to this conventional reflectivity and the radial velocity we get, so we can get a lot of this microphysics information. So then how those information can be used in the NWP, so this becomes a very notable question. So there are two groups kind of publish multiple papers. So this is only two groups work on this dual-pol radar data assimilation. One is from the University of Oklahoma. So they use this ensemble common field. And so they did a very complete process to try to assimilate this polarimetric radar. But the first paper published perhaps 10 years ago, but up to now, we did not see other people use this methodology. And also, the other thing is my former student, Xuanli Li, and her current advisor work on this dual-pol radar with a simple forward model, so warm-rain radar forward operate. So they get some benefit, but so this method is still kind of like, this is just beginning step. So it still needs a lot of work. So right now, I think this morning I had some discussion with a group here, and but I think this is some direction we should still kind of like make a real step in the future. We don't have the best answer now, but given this some of the preliminary study and also the available of the data, I believe we can make the progress. So how we make the progress, I will comment just a little bit later. But in the meantime, so I'd like to give some of this, because we talk about the dual-pol, so we should give some perspectives about the next generation airborne radar. So this is a paper published by this certainly EnKF scientists. It's about the next generation airborne parametric Doppler radar. And so this could potentially use for the hurricane study. So this is a configuration of this proposed C-band radar. So if you look this, so this airborne radar will have the dual-pol component. So then in the future, we will not only see the radial velocity reflectivity, but in the meantime, so this dual-pol component come up, and how can we better utilize this data for the hurricane prediction? So this is really something we need to begin to think about and work on. So I think I just like give a couple of these concluding remarks to finish this talk. So first thing is the airborne Doppler radar is an essential part of observation system for the hurricane research and forecasting. And the second thing is radar data assimilation is still a large area of research and development. Why I say this is last night when I just searched the AMS literature, I into the keywords of radar, I find more than 4,000 publication. So, and then I search radar data assimilation in title. So it's less than 100 paper. So about 54 or something. So is radar data assimilation compares the radar science itself still much under the research. So then the quality control issue and also how we better utilize this information and also develop the workable and reflectivity data assimilation methods, which we can eventually use for the operational still, is posed a large area of research. Dual-pole radar data assimilation is also a new area. So if you search this dual-pole radar data assimilation, you find even less paper available there. And so, as I said, for the dual-pole radar data assimilation, it's just begun, and my feeling is really we need a lot of research in this area by close collaboration between the radar observational scientists and the NWP scientists. So these are the key to make the ultimate improvements, because I think there are observational world, so we have many of these observation tape. So these observations are not direct model variable. So in terms of the model, we have this parameterization. So especially for this microphysics scheme, we have many of these parameterization. Each of scheme has different parameters. And how can we match this parameter and all this parameterization scheme to produce Simpson observation give us? That's the question. And also, if given the uncertainty of the scheme, how much information we can use. And also, can we partially, with the current capability, can we partially use those observations? So that's all the question. Really, I think the thing is we need to begin to have this observational scientists talk with NWP and the data assimilation scientists to make this happen, because we need to work on the same thing, and then so seeing the same picture and making the progress. So I think that's really a very important step. So I would say, so in the future, we should see the equal number of data assimilation paper compared with this radar observation paper. That will be fair enough the time for the use this radar data in the NWP. Okay, so this is all I have. Thank you very much for your attention.
Thank you very much for a very interesting talk. Are there any questions?
So as you indicated, there's a number of technical aspects of radar data assimilation that make it difficult for your average person to use it, such as the massive amounts of data that radar create, to the forward operator, and sort of the complexity of the modeling system. If it's 4-dimensional versus just 3-dimensional. So my question is, which of these do you think needs the most attention to make radar data assimilation more easier to use and more approachable to your average model user?
So I think the simple answer is we need a good data. So that's I think it's more related to the data quality control. So how we quality control the data to be more suitable for the model to use. Because as I said, the model physics has been parameterized. And so then there are uncertainties there. But how we process the data in the way we can use, that could be very helpful.
Any other question?
From what I've read, the NextRad system has elaborate quality control measures are taken, especially for the MRMS product, which is the nationwide precipitation product. So I'm not sure how far more we can do to improve data quality.
Yeah, I think this is very good comment. So yeah, I think that we're seeing now in terms of the radar reflectivity and the radar observation, so this precipitation estimation becomes essential, and then made a really big step there. But the only thing is this precipitation. So we are still we are still have the problem to assimilate this precipitation data, and the precipitation data also is an estimation from the reflectivity. From data assimilation standpoint, we prefer to use the reflectivity, but there are still not the perfect method for us to build up this forward model. That's limit our ability. And also the microphysics uncertainty contribute part of the problem.
Any other question?
You showed a graph of the different model runs that had different microphysical conditions, and I was wondering if you could explain a little bit more about which of those you thought had the best results.
I think for the that's in our early paper, but I think NCEP scheme tends to be in the perform better. It's more complicated case perform better. But surprise thing is, so the Kesslin warm ring scheme actually perform much better. So I think it's sometimes you get good results for wrong reason. So this is not surprise in terms of the microphysics.
The Kessler scheme worked the best. Okay.
Yeah. But this is just for one case. Other case may be different. Yeah.
Where do you think the dual polarization data is going to be most beneficial? Do you think it's in enabling a better specification of like the heating and cooling profiles that you then have to include in a model along with the microphysical information in order to have the dynamical adjustment, or what is it about the dual polarization data that's going to give us something beneficial that we can't get without those data? From a data assimilation perspective, specifically?
I think what's the dual pol added up is some of this classification of this cloud properties. So I think this could potentially help improve the model parameterization. Eventually, we hope to get the better assimilate this information. But in terms of this heating and dynamic profile, I think that's depend on the not only just depend on the physics, but also depend on the inner dynamics of the model. But latent heating is a part of things we should get right. Once we get right, this macrophysics or the phase change of the water inside of the cloud, all those things. But I think this is pretty much details. I would say it's now the most difficult thing is how we relate to the model, what model has in terms of macrophysics variable to this observation, because they're not equal. So, and also model perhaps has less of this variable than the observation have. So how much we can extract the information from the observation, at least partly. And so if we can use this information right, so it will be benefit. But if we just try to say that, okay, here is observation, I want to use them all, so it's not going to work. So I think we still have a long way to go in terms of this. But I think from the current, what I have seen so far, as I said, have the observational scientists talk with the data assimilation people and also modeling people all together would maybe help make some good step forward.
Any other question? If not, then thank you very much again.
Okay, thank you.